All right, let us begin. Hello, everyone. Welcome back. Hope you had a great long weekend. Don't we need more long weekends in the year? Like, it's just too few of those. Like, I cherish every single one, but they fly by, and then you're left with just a regular weekend. What a shame. All right, so before we move on to do a quick review of our last class and then continue with this class, I wanted to make a quick announcement about quiz and homework. So a lot of you reached out to your TAs for quiz solutions. So we cannot make quiz solutions available to you because we reuse these quizzes, and for one reason, and the other reason is if we give you immediate feedback because we give you a couple chances, then there is a chance that like somebody shares their solutions, so it wouldn't be fair, right? So we cannot give you immediate feedback, unfortunately, on quizzes. But what we can do is to, after quiz is closed completely, then we can go in and then do adjustment. Actually, TAs have figured it out or are in the process of figuring it out to tell you which one you got wrong and which one you got right, right? And that way, at least you know which one you got wrong, and then you can, if you can either figure it out by yourself or talk to others, or you can reach out to TAs to get explanation, right? But we cannot give you immediate feedback because of the multiple tries. So we thought about it before class, or before like coming up with this policy. We could give you one try, or we could give you multiple and give you delayed feedback. And we thought that most of you would prefer multiple attempts over just one attempt. So that's the logic behind it. But we are going to we're going to allow you to learn which ones you got wrong so that you can figure it out for exams or for yourself. And for homework, we try to give some feedback, but keep in mind the class is very large, 150 students, and we are committed to give you again some level of feedback, but it may not be very detailed as much as your other classes you may get in other classes, and that should be understandable given the size of the class. But we try to at least give some level of feedback, like maybe a note or like why you missed something. Unfortunately, it's going to be very basic what we can provide, but you can be sure that we are using a rubric for grading, so everything is going to be fair across all students. But then if you see that if you think something requires more attention, that's why we have 2 office hours. So make sure you either log into the Zoom room, right? That's provided for online office hours, or you go to the on-campus office hours to ask a simple question of what happened here or something. But again, remember that you have 2 weeks to reach out and get some clarification on why you missed something, or fix the grade. Essentially, you can always reach back and see why you missed something to learn. But for fixing grades, you have 2 weeks. So make sure you check, you go over it, evaluate it, what you missed, maybe touch base with your TA. It can be as simple as a quick email, or it can be popping into the office hour, and then just asking for feedback. So those are your avenues for getting feedback. Again, because of the structure of the class and the size of the class, unfortunately. Any other questions about quizzes and homework assignments? All right, good. Any other question about anything in general? Any kind of policy that's unclear or good? All right. Okay, so we spent half of last class going through our coding, and hopefully you got more exposed to it during your homework assignments, and then we're going to come back to it. But this class, we want to focus our attention on probability and basics of probability, and we're going to talk about an array of stuff. Most of it is like we're going to go through it very quickly because I'm assuming that most of you have seen this before, maybe within the past 2 years or something, but it's good to remind you of the basics and the details and the terminology. But this is going to be more of a refresher than in-depth explanation of why things happening someday. If you think you're lost, or if you think some concepts are not clear, I recommend you either go through the examples that we cover in class in more detail, or go back and check your priority books. You went through classes either with me or others. I'm sure they have covered all of the things that we are discussing today in depth in those classes. So this was supposed to be a prerequisite, but I thought it's good to make sure that we are all on the same page moving forward. Okay, so we talked about sample versus population last class. Which one do we typically use in reliability engineering? Samples. Okay, so we talked about a lot of different metrics that we can collect from our samples, right? We talked about sample mean, sample median. Okay, so mean is just we add them up and divide by the total number of samples, right? Median is, how do you get median? Quickly. Middle, how do you find the middle? You have two steps. You find the middle, that's the second step. But before that, you have to do something with it. Okay, so let's say I have these three numbers. Let's say 5, 1, 10. Is 1 the median? Okay, so you're doing something in your head, what it is that you're doing. Yes, perfect, exactly. You sort them and then you find the middle one. So it's the 50% rank. Okay. What else? We talked about range, min, max, right? In R, the function range gives you max minus min, same thing. All right, so we talked about variance and standard deviation. Anybody remembers the formula, the notation we use for it? What's the notation we use for it? For variance. What's the notation we use for mean? That's for population. Okay, mu x bar, perfect. So let's go to population. For population, what do we use for variance? Sigma squared, and standard deviation would be sigma. So for sample, what is our notation? S. I heard S. I accept S squared. Okay. So what was the formula? I know it's open note, open books, but it's good to have like these basic things. It's good to have it at hand. Okay. And you can refer to your notes when you're responding to me, because bottom line is you should be able to find it in your notes, and then you're good, right? Okay. Yeah, what was the formula? No one? Uh-huh. Perfect. Over n minus 1. Okay. Which also has another formula, summation of xi squared minus nx bar squared over n minus 1. Okay. All right. Just again, know where they are in your notes, because you may need them in the test. All right. So then we start talking about probability, basic probability concepts. When I say probability, you can immediately think of a dice or a die, right? So we talked about the random process. Anybody want to take a stab what the random process is? How did we define it? Think of a die example. What are the possible options I can have when I roll a die? 1 through 6. What do we refer to that? What? Okay, each of them can be events, so I'm going to get there. But then a collection of everything that I can get. We call that sample space. I heard it. Okay. So the collection of all of it is sample space, right? Before rolling something, what are the possibilities? Everything in the sample space, right? So that's why it's a random process. I'm doing the same thing. I'm rolling the same die. I know the possible outcomes, but I don't know which one exactly is going to come up with certainty, right? That's why it's a random process. Okay. So each one of them that may surface, right? I may see a 3 or a 4 or a 1. What do I refer to that? They're called possible outcomes. Okay. So these outcomes, collection of them or a single one of them can be called events, right? Because, okay, so what is an event? I can observe an odd number. Is that necessarily the observation that I'm getting? I may observe 1, 3, or 5. But the collection of them, I can refer to them as events, right? My event may be simple, right? Observing a 3. Or my event can be compound, right? Observing an even number. So these are, again, terminology. So, okay, so events are a collection of items, right? Technically. So collection of items, another word for it is set, right? So that's why we started talking about set theory. So events. They can be simple, compound, or null events, right? No. Okay. Then we said, okay, now that we are dealing with sets, right, with collection of outcomes, with events or sets, let's just refresh our memory about set theory. So we said that, okay, so if I have a set A and a set B, this is their union. It means that all items in A and all items in B, right, or both. Then we said, okay, if I have two events, then I want their intersection. There will be whatever it's in this intersection is in both A and B, right? Then we said, okay, there is a relationship between a few of these sets. Let's forget about P. So for instance, if I have A union B, these are the fundamentals we covered. It's the same as B union A. Or if I have A union B union C, this is the same as A union B union C. And then if I have A union B, let's say intersection C, what was this one? A union B intersection A union C, right? And the same with when we flip this or we switch union and intersection. What else? We also looked at De Morgan's law. So A union B prime, what is that? Yes, you distribute prime. So A prime intersection B prime, right? Or if I have A intersection B prime, then what is that? A prime, perfect, union B prime, right? My scales. Okay, and we're going to use some of these again today, so that's why I'm doing the reflection. Okay. All right, it doesn't write. Oops, A prime, A prime, union B prime. Okay. All right, so that's why we went and studied or refreshed our memory about set theory. Okay, after that, we started talking about probabilities, right? Now we have a set. I want to associate a quantitative measure to it, right? A value. What is the criteria for this value? Let's say I have event E. P of E, what are the values that I can assign to P of E? What is the range? Perfect. It can be some number between 0 and 1. So this is the first axiom that we looked at. What was the second axiom? If I have a bunch of EIs, simple events, what do I know about the summation of all of PEIs? In my entire sample space? Exactly 1. Okay. If I have the union of a set of mutually exclusive events, if I have their union, and I'm interested in the probability of those, what is that? So think about it. Let's go back to the die example, right? We have odd events, for instance, right? Or like the event, like getting a 2 or a 4 or a 6. Right? These are even. Getting a 2 or a 4 or a 6, right? So those getting a 2, 4, 6, those are my mutually exclusive events, right? What is the probability of seeing any of these? Would be probability of getting the first one plus the probability of getting the second one plus the probability of getting the third one. So essentially, we know it now. I'm formalizing them, right? If I have a bunch of mutually exclusive events, I'm interested in the union. I'm interested in the probability of their union. Then I can simply write it as the summation of the probability of the individual events. Right? The probability of these events, the same events. So we also talked about complement. So if I'm interested in probability of E prime, how can I characterize it in terms of probability of E? Perfect, 1 minus P of E. Okay. Then we talked about mutually exclusive events. Let's say more explicit. So I have these two are mutually exclusive. Okay. What do I know about their intersection? 0. Right? Because essentially to the null set, what is their intersection? Null set, right? So I'm assigning the value 0 to the null set. That's my association, right? So that's what it is. Okay, if I have A and B, if I'm interested in the probability of A union B, what is this formula? P of A, exactly, minus P of A intersection. Perfect, exactly, right? This was the ultimate formula that we came up with, which we showed also with Venn diagrams, right? And so this is it. There we have it. Oh, we had one last formula. What do I know about P of A intersection B if A and B are independent? If they're independent, what is that equal to? A. Probability of A times probability of B. Perfect. That's it. So this essentially summarizes everything we covered on probabilities last time. Now we're going to build on them. Any questions about these? Any of them? Anything unclear? Good. Moving forward. All right. Let's move forward. Okay. We started talking about conditional priorities. You remember we played a game with the doors and everything. When piece of information was given, the priorities, we showed that statistically and also with logic that the priorities change, right? And then, so let's refresh our memory again more formally about conditional priorities. So let's look at these two events. You toss an odd number, that's event A. B is you toss a number greater than or equal to 4. So what's probability of A first? If you roll a die, what is the probability that you toss an odd number? 0.5, a half, okay. So now I'm asking you a different question. What is the probability of A, or observing an odd number, given that the number that has turned up is greater than or equal to 4? So let's see what happened, because a lot happened here. What was my sample space before? Then I roll, just simply I roll a die. What is my sample space? 1 through 6, right? Then I tell you that B has already happened. A number greater than or equal to 4 has emerged, right? What is my new sample space? 4, 5, and 6, right? This is my new sample space. So now I don't need to worry about 1 through 3, right? They haven't happened. I don't need to worry about them. Now I know a number like greater than or equal to 4 has emerged, right? Now, given that I'm giving you that information, and you know that you rolled a die, each side of which was equally likely to turn up. Now, what is the probability that you observe an odd number? In what case do you observe an odd number? Then you observe a 5, right? What is the likelihood that you observe 5 in this new sample space? 1 over 3. Because they were equally likely to happen. I told you that a number greater than or equal to 4 has happened. So now it leaves you with 1/3 for the probability of observing an odd number in this new sample space. So the new piece of information here changed your probability. The same in the door example, right? With the door and the game show problem. So the new piece of information changed their probability. Okay, so this is what may happen sometimes. And why is it relevant to our cause? Why is it relevant to our class? So for instance, think about like you're acting now as for instance, a quality engineer, right? You are looking at your production line and you see that your defect rate is at about like 10%, right? Maybe you want to decrease it to 7%. So you may start by looking more closely into why you have 10% defect, right? Let's say you have you start looking at the samples and you see that out of every 100, on average, 10 are faulty, right? And then if you look at it, like let's say 50 was built in on machine A, or like went through that part of processing, and 50 went through machine B, right? But then out of the 50 that went through machine A, maybe there are 10 that are faulty, or that there are like 7 that are faulty, right? Whereas out of the ones that went through machine B, there are only 3 that are faulty. So that may be a good indication that, oh, maybe there is something wrong with machine A, I need to fix it, or that is I need to target that to be able to decrease my overall like defective rate, right? So but what are you doing? Essentially, you're looking at conditional priorities, right? You're saying, given that I have this, like for instance, the probability that something is faulty or not, why that happened, what was the underlying reason, what contributed more to something being faulty or not. Does that kind of make sense? We're going to look at examples in a little bit to more closely play with them. But this is the motivation behind it. And we show A given B with a horizontal line, or sorry, a vertical line, right? So that's A given B. But let's look at Venn diagrams, because they typically help with understanding or visualizing things. Let me draw a Venn diagram here. This is A. Let's say I assign a priority 0.3 to it. So P of A is between 0 and 1, right? Or more specifically, P of A is 0.3. Now let's say I introduce a new set. Let's say I introduce event B. Let me introduce event B. All right. Let's say this is 0.2, this is 0.1, and this is 0.3. So what is probability of B here? Just play along. 0.4, agreed? What is probability of A intersection B? 0.1, agreed? Okay. So now let's say I tell you that event B has happened, right? What do we do? It's as if I get a cutter, right? I cut through event B. I ignore everything else in my sample space. Now, event B is my life. That's my new state space or sample space. Okay, so now I have event B. This is B. Okay, and of course this was 0.1, and this is 0.3. Now I ask you, what is the probability of event A given that event B has already happened? What is that? What's the probability of event A given that B has already happened? Tell me numerically. Let's first put it numerically, then we come up with a formula. If just forget about everything, like just look at that circle. If you look at that, what is the probability that A happens? Given that one, so remember, let's go back to B. What is the probability of B? 0.4. What's the probability of A total? I'm looking at this. 0.3. What's the probability of the intersection? 0.1. So every number goes to the area the closest area in which that number is enclosed. So that's my convention. So coming back to this figure, what is the probability of A given that B has happened? Okay. So I want to claim that it is 0.1 over 0.4. Do you agree? The total area is 0.4, right? And I'm getting slicing a quarter of it, right, for A. Do you agree with the numeric one? Okay. So now let's see how we got that. Then let's look at the numeric one. So this 0.1, you agree that this is the same thing. This is P of A intersection B. Right? What about this? What is this point for? Do you agree that this is P of B? So essentially, this is kind of the visualization of what we are doing when we are using conditional priority. We are narrowing our focus on that event that has already happened, and now we are looking at the proportional likelihood of this intersection of the two happening, right, within this new set. Okay, so that's our formula. So probability of A given B, I'm going to write it as probability of A intersection B over probability of B. Okay, so if what do you say about probability of B given A? This would be equal to turn it around. Okay, turn it around. You have B intersection A over P of A. There we go. Okay, let's go back to our example. See if this formula helps us a little bit more. Do it without going into a lot of reasoning, just using formula to calculate this probability. So here, I'm interested in P of A given B. This is P of A intersection B over P of B. Okay, what is P of B? Observing a number. What is the probability of observing a number greater than or equal to 4? 4, 5, 6. It's half of my sample space, right? So it's just half. What is the probability of A intersection B? Let's see. A intersection B. What is a set? Let's say A intersection B. What do I get? Just a set. I have here 1, 3, 5. Here 4, 5, 6. What's their intersection? Okay. So what is the probability of observing a 5 when I roll a die? 1 over 6. 1 over 6 over 1 over 2, 1 over 3. So I didn't need any in-depth reasoning. I could just simply, straightforward, use the formula and be done with it, right? So that's the benefit of the formula. Okay. So now that you practice a little bit more with basic conditional priorities, this should be very quick. So take maybe like a couple minutes. And then we can go through it on the board. Meanwhile, if you have any questions about what I just covered, I mean, with the speed of light, just raise your hand and I'll come to you. Okay, what did you get for the first one? Let's see. Let's have a volunteer from that side of the class. 125. Over something, right? Over what? Yes. Okay. So walk us through your logic. 125 over 137 is the correct answer. So tell us how you got it. So it will be this. Okay. You have f, which is okay, which is exactly the summation of these two. Right? So essentially you divided the black by the red. Right? Okay. Let's look at the next one. F over E. Does the numerator change? Doesn't. Okay. 125. What is the new denominator? Exactly. 132, which is essentially the summation of these two this time. Right? All right. Last one. We already have it, right? What is that? Go for it. What is that? No one? Anybody from this side? I'm using the previous for sure, but 1 minus. Exactly. Right? It's complement. Does it matter that I have a condition? No. Remember, I still have a sample space, right? It's just smaller. The same thing with complements stay. Right? So P of f prime given E is exactly equal to 1 minus P of f given E, because before I had P of f, for instance, is equal to 1 P of f prime is 1 minus P of f. So the fact that I changed my sample space, traded it for a smaller one, right, given E, for possibly E is smaller than the entire sample space, it doesn't change it. The relationship between complements stay. So it's just 1 minus the part B. Make sense? Actually, I had the whole thing, but we did it very quick. All right. But okay, when we talked about conditional priority, we said sometimes introducing new information changes things, but sometimes it doesn't, right? I give you some piece of information, it's irrelevant, right? It doesn't change the priority of the events that you're interested in. In that case, again, we come back to the concept of independence. The two events are independent of each other. So the new information here, B, that I gave you, didn't change anything about P of A, right? So P of A given B is still P of A. Okay. So if P of A and B are, if the events A and B are independent, then I know that A prime and B are independent, B and A prime are independent, B prime and A prime are independent, right? And this is very important because you can easily work with a lot. Now you have a lot more at your disposal when you are dealing with priorities and events. So we are not going to go through the proofs of this. Okay, so recall that P of A given B is equal to P of A intersection B over P of B. Okay, so what can I say about P of A intersection B now? So I can rewrite this equation into P of A given B times P of B. Agreed? Make sense? Okay. You may know this equation as chain rule. right? We refer to the whole thing as multiplicative law of probability. So you can go through it step by step, B, A given B, and so on. Okay. So if you have A and B to be independent, then this is what happens to P of A given B, right? And then this becomes simply the formula that we knew before, P of A times P of B. So this is the reason behind it. This is the more general equation for it. Good? Okay. All right. So we have that rule for more than two events. If you have a series of events, all of which are independent of each other, the probability of their intersection is simply the multiplication of all individual probabilities. Right? This is multiplicative rule, the rule of probability. Okay. All right. So let's look at an example. I'll give you time to go through it and give me the answer. Let's quickly look at the word choice. It says, what is the probability that at least one of them is received? Right? What does at least one of them received mean? It means that maybe the first one is received, the second one is received, the third one hasn't received. Or maybe the first one received, the second one hasn't received, the third one hasn't received, right? Or maybe all of them are received. So there are a lot of combinations if you want to go at it straight, right? One is received, two are received, three are received, right? Whereas when we say at least one is received, how else can we look at it? It's the complement of none is received, right? So look at it that way. It will be 1 minus the first one hasn't received, and the second one hasn't received, and the third one hasn't received, right? And that way you're also introducing the concept and, which we know things are independent, so we can easily multiply things there. Okay, so we are essentially saying, we are essentially using De Morgan's law, right? Because we are saying it's 1 minus, or we are saying, okay, so A union B union C, right? We're saying, oh, that's too much work to calculate. So we are doing the complement of that. So we are saying this is the probability that none is received, 1 minus P of A prime. Let's say if A is, first one is received, the second one received, C, third one received. We are saying this is 1 minus probability of A prime intersection B prime intersection C prime. Right? The first one hasn't received, and the second one hasn't received, and the third one hasn't received. Right? What is the probability of, let's say, A, B, and C? These are all 0.85. So their complements will be 1 minus 0.85 or 0.15. So this is A prime, B prime, C prime. Right? So this will be 1 minus 0.15 to the 3. That's it. So pay attention to keywords, because we're going to use a bunch of keywords in our class, at least, at most, exactly. Right? So these keywords matter a lot. Good? Clear? All right. So if we have 3 events, A, B, and C, all mutually independent, then what do you think we can say about the probability of A union B given C? All right, let's look at it. So do you agree I can write this as, let's see, P of A union B given C? Do you agree I can write this as 1 minus probability of A prime intersection B prime given C? Do you agree that's the same? Do you remember we had this P of F prime given E is the same as 1 minus P of F given E. Right? So I'm writing A union B prime as A prime intersection B prime. I'm using De Morgan's law. Okay, if you agree with this statement, the rest is simple. I can write this as 1 minus P of A intersection B intersection A prime intersection B prime intersection C over P of C. Because they are independent, I can write this as P of A prime, P of B prime, P of C over P of C. These two simplify. Then this is 1 minus P of A prime intersection B prime, and this is P of A union B. Okay, I don't expect you to be able to go through the equations as quickly, but what I want you to remember is that this is equal to that, given this, which means what? What does this equation imply? The fact that P of A union B given C is equal to probability of A union B. It means that A union B is independent of C. So we're going to use this very exact property in the next example. That's why I showed it to you, because I want you to use it. Right? So as long as they are all mutually exclusive, you have that condition. Make sense? Good? Okay. So then let's move on to this. Let's go through the question together, and then because I want to comment on that. So let's see. An electrical system consists of 4 components as illustrated below, right? We have A, B, C, and D. The system works if components A, B, and either of components C or D work. So we showed this sentence with this kind of representation. Later on, we're going to go through this kind of representation a lot. Essentially, half of our class we're going to spend on these representations, right? And analyzing the systems like that. These are called reliability block diagrams. Right? We simplify systems in form of boxes, in each of which we write the reliability of that component up to that particular time that we're analyzing. Right? And then we analyze the different relationship between them. They may be serially dependent. They may be in parallel. They may be complex combinations, right? So there are going to be a lot of time you're going to spend on these systems or simplified systems where we show them with blocks, reliability block diagrams. But then if this, and again, we haven't gone through this a lot, just know that this is the representation for that. But you can essentially, for this example, you can only look at this. So this will be your introduction to reliability block diagrams. Okay, so and we assume, in these cases, we assume all components are independent of each other. So given that this information that are written in each box shows the reliability of each component, what is the reliability of the system? You should be able to calculate that right now. So I give you a little bit of time. Don't worry, you can talk to each other, you can ask me, but I want you to start thinking about it. So you have 4 events, A, B, C, and D. And the system works if A works and B works and either one of C or D works. So start from there. Right? That should be quite straightforward. Okay. So why are you using condition? All right, a lot of you got it. Great job. So let's look at it. Let's calculate what we see here. So it says, all right. So, okay, A and B, either of the components do it. So I'm going to just write what it says. A happens, and B happens, and C or D. Right? This is it. Okay? So now I want the probability of this event. Okay, with intersections, I'm good, right? I know A and B are independent of each other, but last slide we also showed that when I have C or D, this union, like if I have all events being independent, then the union of a couple of them is independent also from the third event and the fourth event, right? So all of the events right now, A, B, and C union D are independent of each other. Agreed? Okay, so if they're independent, I can just multiply them. So I can write this as P of A times P of B times P of C union D. Okay, that's the step one. Agreed so far? Any question on why we're allowed to do this? So what do I know about this? I can either calculate it from this, P of C plus P of D minus P of C intersection D, Or I can calculate it with 1 minus P of C prime intersection D prime. They're the same thing. Agree? I'm using De Morgan's law. Let's verify, actually. So what is, so let's first calculate these. What is P of C? 0.85. What is PD? 0.87 minus, what is P C intersection D? I know that they're independent. I can just multiply them, right? 0.85 times 0.87. Can somebody tell me what that is? A little bit louder. 0.9805. Let's check the other one. 1 minus P of C prime times P of D prime. Right? This is 1 minus. What is 1 minus 0.85? 0.15. What is the other one? 0.13. Can you tell me what that is? Okay, so I was right. And De Morgan's too. Okay? Because what did I do? I said C union D prime C union D prime is the same as C prime intersection D prime. Right? So I used complement because what do I do? What do I need? Because I can multiply probabilities when I have independence. I want intersection so that I can multiply things. So that was a trick I used. So anyways, so now I have 0.91 for A, 0.93 for B, times this new number 0.805, and then I get I think 83, and I'm rounding. So this is it. So this is just to showcase everything we learned, right, so far. Law, like we learn about independence here. Independence of the union of two events from the third event. De Morgan's law. The use of events, right, and set theory when we are calculating probabilities. So everything that we are learning is for a purpose. It may not appear right away to you that we are learning it for a reason, but then we can bring them all together under one question. All right. Any questions about this? All is clear. And we're going to come back to these. So if this is too difficult, this was supposed to just showcase what you're going to learn later, right? And you're going to be proud of yourself because you're going to be able to solve much more sophisticated reliability block diagrams than this. But then this was just a taste for now. Okay. All right. So let's quickly go back to Venn diagrams because I want to introduce or reintroduce essentially Bayes theorem. You all are familiar with Bayes theorem, but let's refresh our memory about it. So we have a Venn diagram, let's say, with 4 events on the sample space. These events are, I'm assuming they are mutually exclusive and exhaustive. So what do these mean? Mutually exclusive, there's no overlap, right? Exhaustive means they span the entire sample space. Okay? So this is, for instance, a set of 4 mutually exclusive and exhaustive events on the sample space S, right? They are mutually exclusive because there's no overlap, there's no intersection, right? And they are exhaustive because I'm covering my entire sample space, at least visually, right, with them. Right? So if I have a new event B, right, on top of this sample space, do you agree that I can characterize this event B in terms of this little piece, this piece here, this piece here, and this 4th piece? Do you agree that I can do this? Right? And if I can characterize, if I can come up with these events, these little events, green, yeah, I don't know, red, blue, right? If I can come up with those events because they are mutually exclusive, the probability of B will be just the summation of the probability of those four. Okay. So what is this blue one? Do you agree that this is probability of B intersection A3? Right? Okay, let's look at the other one. Let's see if we can do all of them. This is probability of B intersection A4. Right? Okay. Let's see. What is this one? Probability of B intersection A2. Right? And last one. Actually, this one, this little one. What is that? Probability of B intersection A1. Right? So the events are A1 intersection B, A2 intersection B, A3 intersection B, A4 intersection B. Right? The probabilities are the probability of each. So I can write B as the union of these four intersections. Right? So the probability of the union will be, which is B, will be equal to the summation of all these little probabilities. This is it, right? Probability of B, I can write it as a summation of probability of B intersection AIs. Right? Or alternatively, I can turn this around a little bit. So let's see. Do you agree that I can write this as probability of B given AI times AI? This is what just we learned a couple of slides ago, right? So I can write this as P of B given AI times P of AI. Right? This is it. This is law of total probability. Quite simple when you look at it visually, but it can get maybe hopefully not confusing, but it can get confusing when you look at it like in terms of like a question that you want to transform into math notation. But this is the essence. This is law of total probability. Okay, so with this and with what we learned earlier, we are on our way to look at Bayes' theorem. What is Bayes' theorem? You have A through AN, A1 through AN, mutually exclusive, exhaustive, right? You have a new event, event B. So you're interested in, let's say, probability of one of these A's given B. You can obviously, this is A given B, right? You can obviously write that the intersection over the probability of the thing with which you're cutting, right? With the one that's given. In this one, you use law of total probability to transform it in the longer form. And with this one, you're using multiplicative law of probability. So that's it. And you can calculate a probability or a conditional probability that's not necessarily given to you. Okay, we're going to look at a couple examples now. Hopefully that everything will make sense then. Okay, let's look at this. I let you read this. Don't worry about solving it. I want you to come up with events that you think are important, and then just tell me what these numbers are in terms of the events we have. We will come up with two Bayes events and a bunch of conditional priorities from the text. Let's start from the easier one. This is, I think, is the easier one. So if you look at that, what would it be the events that you describe here? That is the probability of your event. So your event will be detector is failed, right? So let me call that F. So failed or failure, failed detector or detector. Okay. So then P of F will be 0.2. Exactly. Okay. So now let's look at this sentence. What is the other event that's introduced in this sentence? Power surge, right? Okay. So now we have also power surge. We can show it with PS. Let's say this is power surge. Is experienced, right? Experienced. Okay. So this sentence, what does that tell us? It says we know that in general, out of every 10 failed detectors of this type, 8 have experienced a power surge. So you can think of it as if you have a QA, right? Like or quality assurance team, right? You give them the detectors, right? They look at the failed ones and say, oh, out of these 10 failed ones, 8 of them has experienced power surge, right? So given that they've been failed, right? They go they dig into it. Like they look at it, they analyze it. They see like what, like maybe there's a burnt something somewhere, there's a melted like metal somewhere, right? That is indicator that power surge has occurred. So the probability that power surge has occurred, given that it's failed, what is that probability? Out of every 10, 8 has experienced power surge. So this would be 0.8. Make sense? Okay. So what about this other sentence? Out of 10 working, 1 has experienced power surge. Can you tell me how you would write that? Failed and working, what's the relationship? Complement. Okay, so I'm going to write it with F prime. Right? I'm not going to introduce a third event. You could, but then you may lose track of things. So it's easier to just not introduce extra events if not necessary. Okay. So what else? The probability of power surge. What is that probability? Given that it's not failed, it's working. That is 1 in 10. Right? 0.1. All right. So we have all three all events, and essentially we summarize the text into notation. Okay. What does the question want? What is the probability that the detector is failed if we learn that a power surge has occurred, given that a power surge has occurred? Right? Before, if we had no information about no power surge, the probability of failure was what? 0.2. On average, because of the noise or something in general, we know that like it is the probability that the detector is failed is like 0.2. Right? Now a power surge has occurred. We have some information from our quality assurance team that had analyzed like all failed and like maybe some of the working detectors after or before some power surge. We have some information, prior information, right? Now we know power surge hit or power surge occurred, right? How would the probability of failure change? So now that's what I'm interested in. So you should be able to easily use Bayes theorem to calculate that. So now I give you a few minutes to go through it, and then we look at it on the board. Anybody got the answer? Too quick? 2/3. Yeah, that's what I got. Okay, so let's look at it, and I give you then 10 minutes break because I didn't realize time has passed. Okay, so f given ps, I can write this as f intersection ps, ps over p of ps. So I look at what I have. I have ps given f and f, so I can easily write this as ps given f times pf, right? And denominator, I'm going to use law of total probability. This will be p of ps given f times pf plus ps given f prime times f prime, probability of f prime. Okay, I plug in 0.8 times 0.2 over 0.8 times 0.2 plus 0.1 times f prime, 1 minus 0.2. So I get 0.16 over 0.24, and I get 0.667. That's it. All right, I essentially went through this example for you. We have 2 more exercises on Bayes' theorem. After the break, we come back, we reconvene, we go through them, and I give you a little bit more time to work through them and ask questions if you have any. Because I understand Bayes' theorem can be one of the, most people complain about it. It's one of the most difficult parts of maybe basic probability. But then I'm hoping that after these couple of examples, you get a hang of it. All right. Let's come back in like 10 minutes or less because we have a lot to cover. Sorry. Okay, most of you are here anyway, so I'll let you look at the next problem and start working through it. We're going to get another short break after we go through 3 examples. So let's work through these. And then I'm showing you a video and like do a pop, like not, it's not a quiz, it's like do a fun exercise and then have a little bit of fun then. So let's get busy. Like this? Yeah. So what is the question one? What is that? All right, I think most of you guys got this one. Let's look at it on board. So we have three events, A, B, C, right? Probability came from A, probability came from B, probability came from C, right? And the probabilities are given. It's 50%, this one is 40%, this one is 10%, right? And then we also know, given that it comes from A or B or C, what's the rate with which it's defective, right? Probability that it's, some of you had it failed, some of you defective, it doesn't matter. So probability that it's defective given that it came from A. Probability that it's defective given that it came from B. Probability that it's defective given that it came from C, right? That's also given by the question. So this is 1%, this is 2%, and this is 5%. Okay? And the question says, okay, now we selected part randomly, we know it's defective. As soon as you hear it's known, it's given, it's established that something has happened, right? That is the given part. So given that it's defective, now what's the likelihood that it's from A, right? Okay, so you see how we have here B given A as part of the information given, and we want A given D. That is the signal that you have to use Bayes' theorem, right? Because you want the flipped version. So you use Bayes' theorem. So this will be probability of D given A times probability of A over probability of D given A PA, probability of D given B PB, probability of D given C PC. You plug in the values, you should get 0.005 over 0.018 equal to 27.18%. You would get something similar. Good, makes sense? Any questions, concerns, comments? Okay, so if you're feeling comfortable with Bayes' theorem, I had another question, but I'm going to give it as a homework or quiz instead, and then skip over it because you're kind of running out of time, and I want to cover these stuff today. So I'm going to very quickly talk about combination, and then we're going to wrap up this mostly refresher, and then move on to again things that you have seen before, but maybe they are more relevant, closely relevant to our class. Okay. So combination. So how is it relevant to our class? We're going to see it very often again towards the third, maybe the second half of the class. But I want to just make sure that you are familiar or you remember the formula. So for instance, if you have a 3 out of 10 system or something, you want to know, so you don't care which one of the 10 items failed. You only care if 3 failed or 4 failed or 5 failed, something like that. So if you want a subset of objects, K objects, let's say, from N objects, how many ways can you pick that subset, right? So if you remember N choose K, right, you should have extensively seen it in your probability classes. Do you remember the formula, how you calculate N choose K? I know if you got 200 with me, and I'm looking at some of you, we had one class dedicated to combinations. No, this is close. What else? You're missing only a little bit of it. This is permutation. Okay, so you're close. So n factorial over k factorial times n minus k factorial. This is the formula. N factorial over k factorial over n minus k factorial. This is in how many ways you can choose k objects out of n objects without caring about order. Okay, let's look at it in action. Here's a quick example. So read through the example and we can go through part 1 together. Or maybe, okay, work through all of it. I come for another round through the class. And let me know if you have any questions. So let's see. It says, what is the probability that none of the two batteries in the sample are defective? How many do you want in your sample? 2, right? How many are defective? 2. How many are not defective? 18. So if you pick your 2 from the 18, then you're golden, right? So in how many ways can you pick a sample of 2 out of 20? 20 choose 2, right? That's in how many ways you can pick a sample of size 2 from a total of 20, right? So that's your denominator, right? In how many ways can you pick 2 out of 18? That will be your numerator. Does that make sense? So again, I'm covering the first one to let you know how to get started. So in how many ways can we pick out of a sample of 20, 2, right? 20 choose 2. 20 factorial over 2 factorial over 18 factorial, right? And in how many ways can I make sure that the 2 that I'm picking, right, is not defective? They should come from the healthy or the good 18, right? So 20 choose 18. So if I want no defective, 18 choose 2 over 20 choose 2. In these many ways, my 2 will be from the non-defective ones. 18 is 20 minus 2, because these are the non-defective ones. Exactly. So these are the defective. This is how it plays out. Right? Okay. So now that you know that, now answer the other 2 questions. You want at least one defective and exactly one defective. Answer these 2. It doesn't guarantee that you get at least one. Okay? Well, I don't get it better. So you know how I was going for? I was going to 1 minus 1. So whenever I see a 3, I go 1 minus 9. Right? But I just say I think you live in much later. You're removing one, as you even from other people. But when you're removing the other one, you from the other one, and then you the other one. So there are integrations as a initiative, the first thing, 1 minus 9. Right? If we calculate the probability that nothing is defective. So 1 minus that is the probability that at least something is defective. Right? So we have part B already answered. It will be 1 minus part A. So always replace at least in your head with 1 minus 9. And then see if that helps, makes it a little bit easier to solve it. No, I think you're right, because there are two options, right? You can say, okay, this one is definitely space, and or like this one is actually space. So there are two ways. Makes sense. But for the third one, you want exactly one to be defective. So you want exactly, so I'm not saying everything in the question. So exactly one is defective, then it means that exactly one is non-defective. Right? You have two. So if exactly one is defective, exactly. So you have to pick one to come from the 18, the other one to come from the 2. Right? That's it? No, 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 no. Okay, so part B was 1 minus part A, right? This is 1 minus this, right? And when I'm saying exactly 1, denominator is the same. Exactly 1 needs to come from the 18, and exactly 1 needs to come from the 2, right? Exactly 1 is defective, and the other one is non-defective. So 1 from each. Question? Yeah, yeah, because it's the summation of all three. This one is defective, or that one is defective, or both are defective. So, but then one of your friends was had a good point that, like, what if this, instead of 2 you had 5, right? Then you have to be adding and subtracting a lot of different terms, right? So it's good to have all of these options because they're all equivalent, but it's good to like do a quick search in your head of which one has fewer terms that you need to calculate, if it's like a time restriction or something. But yeah, you're right. There's another. Okay, so here are a few formulas for your reference, because we will be doing a little bit of integration and derivatives in the second half of the class. Hopefully we get to it. And integration by part, again, for your reference for the most part. It's good to have it in your notes. We may or may not use some of them. But now let's take a quick break and then have a little bit of fun. Fun with priority, and then come back. So listen, because at the end of it, or in the middle of it actually, I'm gonna pose a question, or actually the speaker poses a question, and I want everybody to answer. I want everybody to participate. All right, we are gonna have fun. So listen up. This is a TED Talk. It's a little bit old, but it's still very interesting. Go to this link and vote. And we're going to look at it. All right, so 5 people say A is greater than B, 23, they're equal, 7, A is less than B. Anybody wants to defend their choices? You want to go for it? Why? You need to assume here that the probability is 0.5. So this is like, again, stylized fair coin. Okay? Any other reason for it? Okay, so let's listen to it. Where's my TikTok? Did it open this? Oh no. All right, so I encourage you to watch the rest of the talk. He poses a couple more interesting questions, one of which we have looked at in our priority class, but I find it very refreshing. So I encourage you to watch it. Unfortunately, we don't have time to go through the rest of it, but hopefully you were pleasantly surprised with the answer and the reasoning behind it. So little things that, again, we don't have very good intuition for a lot of probabilistic matters. So don't worry if something seems unintuitive to you or counterintuitive to you or like unnatural, because we are not necessarily apt at understanding probability intuitively. That's why we need all of these formula to go through them systemically to make sure that we can quantify them. All right. Okay, so let us switch gears and start talking about random variables, and then we go back to the realm of probabilities and associate them to that. Okay, random variables, pretty simple. They're functions that put a number essentially on the outcome that we observe. So they're called random because they come from random process, and they have the word variable because the outcome, the value of that function can change. So let's just look at a couple examples. Let's see. For instance, we roll 2 fair dice. Can you give me a random variable? So for instance, I observe 1, 5. What can be a possible random variable? We said random variable is a function, right? This is the outcome that I observe. So my function would translate this outcome into a value. So for instance, a random variable would be maybe add the 2 numbers, maybe subtract the 2 numbers, right? Maybe multiply the 2 numbers. It's a function that associates the inputs to an outcome. So for instance, random variable x may be adding the 2 numbers, then the outcome is 6, right? It's just a function, random variable. Okay. So for instance, when you toss 3 fair coins, maybe it's a number of heads. So if that is your random variable, and you observe, for instance, head, tail, tail, then the number of heads will be 1, right? It's a function. If your experiment is a compressor, operates until it fails, maybe the random variable of interest is how long it lasted, right? Then your outcome will be the time until failure. So random variables, we typically show them with capital letters, right? When we are denoting the random variable, the outcome we show with little x, little y, lowercase version. Okay. So random variables, as you all know, come into the two types, discrete or continuous. Discrete is when they map to a finite set or a countable set. Infinite, or like continuous, where it maps to an infinite set, right? When it maps to a line, for instance, a point in a line from 1 to 3. If it maps to that, if that's the range of your random variable, range of your function, then it's called continuous random variable. So when it maps to real numbers, it's continuous. When it maps to a countable set or a finite set, then it's discrete. Okay, so continuous versus discrete. Just tell me, is this random variable continuous or discrete? The number, it shows the number facing up after a die roll. Discrete or continuous? Discrete. Number of failed components and now into an acceptance test. Discrete. Lifetime of a component. Continuous. Number of working components in a system with redundancy after 10 cycles. Discrete. Number of working hours, right? Number of working components. Okay. So just again, quick reminder, PDF, probability mass function, or probability density function. It is a function, right? I'm not calling it a probability. It is a function, right, where you get the integral from point A to point B, gives you back the probability, right? So this is a function. When you integrate it from between 2 points, point A to point B, it gives the probability that your random variable is between those 2 points. Okay? So for instance, here, I have a PDF for product length. So if I'm interested in the probability that this product, randomly selected product, has a length greater than 95 inches, how can I find that probability using this curve? It's the area under the curve where it meets this criteria, right? 95. This will be the area will be the probability, right? If I'm interested in the length being between 95 and 190, then I truncate it here, and this will be my probability. So I'm integrating under the curve, right? The area under the curve. That is the probability. Okay. So there are two properties for PDF. First thing, the curve is positive. Fx is greater or equal to 0, right? Above the 0 line. And then the area under the curve, the total area from minus infinity to plus infinity, adds up to 1. Right? So what is the probability that x is 100 inches? What is that probability? Zero. There is no area, right? It's 1 point. It's 1 line. There is no area. That's 0. Okay. So this is very important. So as I mentioned, this is just a curve. This is not a probability. So you cannot look at it and say this is the probability. Right? Another question. Let's see. 1, 2, 3, 4. Let's say I have a curve like this. Can this be a probability, a PDF? A valid PDF. Can this be a valid PDF? It's obviously meeting this, right? It's above greater or equal to 0, right? But can that be a valid PDF? No, I'm seeing some nods and some head shakes. No, yes. Maybe? Why do I get maybe? Okay. Maybe, I take maybe. Want to go for it? No, that's a good question. So let me make it nearer. I didn't give you the units on the y-axis. So under what criteria this is a valid PDF? Okay, let me phrase it differently. Can this ever be a valid PDF? Yes, right? Under some circumstances, it can be a valid PDF. When the area is equal to 1, right? If this is scale, let's say this is 0.01, 0.02, whatever, 0.03, right? That can be a valid PDF. You cannot just say, oh, it goes beyond 4, so it's not valid PDF, right? Because it's all about the area. If I look at any area, let's say this area, it's less than or equal to 1. This area is less than or equal to 1. If I sum over all of it under the curve, it's 1, so it's valid PDF. So make sure you know that this is not a priority curve. It's just a curve. It's just a function, right? And you're integrating it. Okay? So if, for instance, you have a question like this, how would you address it? So you want to come up with a value C such that this function is a valid PDF. What do you do? First, you need to check first property. Is this positive or not? Then you have to make sure that the area under the curve equals 1, right? So we start by integrating. So we are integrating over the domain. So if I integrate from minus infinity to plus infinity, the function is 0 outside of 0 to 2. So I kind of forget about that. And I'm going to just integrate it from 0 to 2. C 4x minus 2x squared dx. If I integrate this, let's see, I'm going to get, so what this value I want, what do I want it to be equal to? 1, right? Because I want this to be a valid PDF, right? The total area under the curve, I want it to be equal to 1. So this would be C times 2x2 minus 2/3 of x to the 3, evaluated at 0 to 2. So C times 8 plus, minus 16 over 3, right? Evaluated at 2 minus evaluated at 0, it will be 0. Is equal to 1, which results in C being equal to 3/8. Right? So, and I check then. So if I put C equal to 3/8, is this function positive for x between 0 and 2? The answer is yes. Right? Does the area add up to 1? Yes. So in that case, fx is a valid PDF. Right? You've seen this before. Okay. All right. Okay. So the probability of a single point in continuous word, right? It's 0, which means that probability that x is between a and b is the same as probability that x is strictly between a and b, or maybe it's closed one side, open another side, and so on. They're all the same when you are dealing with PDF only. When you're dealing with continuous random variable. Right? So only with continuous random variable you have this. Okay. CDF. Do you remember what CDF was? Cumulative, right? The first keyword, cumulative. So it's accumulation of the area under the curve up to this point x, right? So from, for instance, minus infinity, or the lower bound of your domain will be minus infinity to x of fy dy, right? This will be the CDF, accumulation area under the curve up to point x. Okay, so it's the density, the area under the density to the left of x, right? Okay. Okay, so if I have a PDF, how can I get a CDF from? So I have to look at every point, right? Let's say this point. I calculate the area up to that point, right? And then mark it on this other one. So area, mark it will be here. So you're going to get, for instance, here a curve more or less, maybe a little bit shorter. Kind of similar to this. I'm not a good drawer. Okay, and then, so you start from 0, and then after this point, you've accumulated everything, which puts you at 1, right? And then you stay at 1 for infinite. So you start from 0, then you go to 1, here. Make sense? Okay. All right, so let's calculate the probability of failure by 200. If this is my CDF, or sorry, PDF. Tell me what you get. What did you get? So your calculators can do this, right? Okay. So what did you get? 0.6. Yeah, I'm fine. You can use your calculators for this. No worries. Open everything. The key is to understand that you have to write this, right? You have to integrate from 0 to 200. Right? Then you have access to your computer, you have your calculator, everything to calculate it. All right. Okay, so reliability function. So speaking of which, let's see. So first, here in this question, what is this 0.86? What is this value? This is the probability of failure happening at some point, right, by our 200, right? So this is some kind of measure of unreliability of your component, right, by 200. So in that case, what is the reliability function? It's if Your failure, whenever it happens after that point in time that we're interested in. So a reliability at time x is the area under the curve to the right instead of the left. So it's a probability that you fail at or after x, right? So you will be integrating from x onward, x to infinity, fy dy. Or it will be 1 minus the probability that you fail by that point. Right? So that's it. So fx, CDF, which we were familiar with, in the context of reliability engineering, it becomes unreliability function. Right? And then reliability function will be simply 1 minus f, 1 minus capital F, 1 minus CDF. Right? It will be the area to the right of x. So what are the boundaries for the reliability function? What are the values it can assume? It can go from 0 to 1. Right? It's 1 minus CDF. So it goes from 0 to 1. Right? It is still a probability. Right? It is a number between 0 and 1. Okay? So if you have a CDF, essentially your reliability function will be something like this, right? Because fx plus rx is equal to 1. Because your reliability function is 1 minus fx. Nothing fancy, right? So, for instance, if you have x to be the time that you're interested in, then CDF, which is this area, would be the probability of failure by time x. And this area will be the reliability. It will be the probability that the component fails at or after x. Right? So it will be the fact that it's the probability that it's reliable by time x. It will only fail after x. Right? So you can easily use like redo a lot of the equations that you've seen before in terms of the reliability function. So for instance, if I'm interested in, say this is A, this is B, the probability that x is between A and B, how can I write it in terms of R of A and R of B? Okay, I subtract off. So I want to write it in terms of R of something, subtract R of something. So what is the first something, what's the second something? So remember, we don't have 0 to B, 0 to A. It's just 1 point, right? Because we are integrating. So what you're saying is actually correct, right? You're saying, let's say we have this area, right? And we subtract from that area this area, right? I can get the blue one using that, right? But the area under the red one, what is that in terms of reliability function? You agree that this is reliability A. What about the green one? The area that I'm marking in green. What is that in terms of reliability function? B, exactly. So you can essentially get that from RA minus RB. So when I'm using the function form of RA or RB, I'm already integrating. I'm integrating under the curve, right? So you can either show this as integral, for instance, here, integral of b to infinity of fy dy, or you can simply summarize it and say this is rb. So this is our notation. Get used to it. RA, RB, FA, FB, right? And capital F has a different meaning than lowercase f, clearly. So just keep that in mind, because you may see again, when you're seeing a question, we are assuming that we are on the same page. Capital F has a particular meaning. Capital R has a particular meaning. Lowercase f has a particular meaning. Make sense? Is that clear? All right, so let's talk a little bit more about the relationship. Make sure that we understand the relationship between them. So, okay, so tell me how I can get capital Fx from lowercase f. How can I get f, capital F, cumulative, CDF, from lowercase f? We just looked at it, right? What do? You integrate. Integrate from where to where? To x, perfect, of, let's say, fy dy. Right? So what about y? Sorry, what about r? How do you get r? Perfect. Okay. So if I want f, x from capital F, how do I get that? Take derivative. dx, dx, there we go. How can I get this from r? Before that, let's look at this. What's the relationship between fx and rx? 1 minus. Okay, maybe that helps you figure out this last piece. You are right with the minus, but the 1 disappears if you take derivative of 1, right? So this minus rx dx. That's it. Right? So we can move from each one of them to the other one. If I give you fx, you can tell me r. If I give you r, you can give me back lowercase f. If I give you capital F, you can give me like, right? So you can reach from each one to the other one, right? And calculate everything. Make sense? Good? Okay. All right. So in this example, we had f be equal to 0.865 last time we looked at it. Now, if I ask you what is the reliability, then you can tell me what exactly is the reliability, right? Because we have a relationship between capital F and capital R, right? Just the last slide. Okay. All right. Okay. So in this case, find R at 1.5 for this example. Not it. What do you get? That is what I get to. Yeah. All right. So again, this is a formula. You put it in your calculator, you calculate it. But I want to tell you, I want to speak a little bit about this. Sometimes it helps, instead of calculating for the numbers, calculate the function. And if I, for instance, ask you, give me R of 1.5, give me R of 1.8. If I ask you multiple questions, it may be faster if you have a function, then you plug in the value. So you can calculate the function using this, and then plug in for x, plug in 1.5, 1.8, and so on. But the other question I have is, what is R of 0 and what is R of 3? What's the reliability at time 0? 1. You haven't lost any reliability yet, right? Reliability at -3. It's 1. You start with full reliability, right? You go through 0 to 2, you start losing reliability because you have a probability of failure, right? By time 2, you're sure that your system is failed, right? So what is the reliability at 3? 0, right? Things have failed. So reliability at 2, 0. Between 0 and 2, so this function you're going to write is for reliability when your x is between 0 and 2. Right? Below 0, you have full reliability, 1. After 2, you have no reliability, 0. Right? Because you have gone through, accumulated all area under the curve. Right? With probability 1, your system is failed. All right. So let's stop here, because I don't want to go through the all full length of the class. That will be too much. We're going to start next class with design life and review some of the stuff and move on with the new stuff. Watch out for quiz and homework as always. All right. Have a good weekend. You too.